Welcome. I'm just going to jump around the screen a little bit. So welcome to Wednesday lecture. So a lot has gone on since we last were together. So more specifically to our class, you've taken a midterm, but more broadly, we obviously had an election last night. And so we have a lot to talk about. So today I do want to turn our attention to chapter 10 and kind of get our heads wrapped around what we're doing here in chapter 10, what types of questions we're trying to answer, and really chapter 10 and 11. So just to kind of start that discussion, chapter 10 and 11 are kind of a pair. We're doing very similar things in these two chapters. So kind of like 6 and 7 were linked together. 10 and 11 kind of go a little bit hand in hand. So we'll turn to that. We'll kind of try to structure what our process is going to be in chapter 10. And we'll depending on time, maybe we'll finish kind of one full example, but we'll spend more of our time on what are we trying to do, how are we going to do it, and then we can spend more time on Friday looking at examples. So before we jump into more detailed course material or election material, I mentioned this in an email, but just to reiterate a few of these things. So chapter 10 is rather large, and there are some new concepts that we're going to have to struggle through. And so post-exam and post-election, I don't expect all of you to have, really dug into the material yet. And so I've pushed back the due date on your Connect assignment till Tuesday. Now, with the knowledge, though, that this is a big chapter, and so, I hope that you won't, put it off till Tuesday. And in fact, because it's rather involved, it probably won't be a pleasant experience if you do try to, cram your assignment in the last few hours of Tuesday. So please do, get back into this chapter relatively soon. Obviously, post-exam, I take some relax, take the evening off, and I'm sure there's plenty of things for you to shift your focus to. So that, but then we will jump back into our typical flow of Sunday night. So you can anticipate chapter 11 being due that following Sunday. So in whatever that is, 10 days. And again, chapter 11 kind of pairs nicely with 10. So hopefully it'll flow quickly to getting you back up to speed. So more broadly, if you're trying to plan kind of the rest of our time together, so these are two big chapters that we have, and then we'll have a little bit more time left, maybe another week and a half or so, I think. And so after we're done with, after we're done with chapters 10 and 11, we'll shift our focus to a concept called regression. And so that'll mainly be pulled out of chapter 13, but probably what we'll do is look at most of chapter 13 and a little bit of chapter 14. So we're going to skip chapter 12. So if you're trying to look ahead and plan ahead and read ahead, skip over chapter 12, and then we'll pull some kind of specific areas. Again, most of chapter 13 and a few dabblings in 14. And that'll pretty much bring us to the end of our time. Other things to keep on your radar. So we are turning now, the chapters 10 and 11, and then the regression material lends itself well to seeing Excel in action. And so you can anticipate a couple more problem sets. These will be shorter, with just the focus on seeing Excel perform these tasks. We won't spend as much time, trying to learn Excel other than what we specifically need for this. So, but those will be out there. They'll be shorter. But yeah, plan on just a couple of those as we finish up the semester. And then of course, which I think is true for all of your courses, we finish up around the 25th of November as far as coursework here, and then we have what are we calling it? The reading week or something. There's a period where you can review and kind of study up, and then we'll have our final exam. And the date, I think, is either the 8th or the 9th. It's in the syllabus, but we'll do a similar thing where you have a period of time to work on the take-home exam. So that was a lot of kind of reframing where we are. Yeah. So, and if you have questions, please feel free to email me or swing into office hours and we can chat more about that. So before we turn to chapter 10, I do want to just discuss a little bit of what we saw last night and potentially some things we can learn from our kind of statistical side of things. And as I mentioned, if you have questions or thoughts, please feel free to raise them. We can talk about it. None of us know all that much. It's early to know. There's a lot we don't know yet. But happy to chat about it, and we can try to figure those things out. So, what did we see last night? What did we learn? So probably the big takeaway is that polling is difficult. So in chapter 9, we kind of tack on polling here at the end of this sampling chapter, and it fits really well. The methods are the same, but one thing, sorry, there's alerts in the corner and they're distracting because it's about the election. So one of the things that we kind of brush over, and we made note of this, is that we're making a lot of assumptions when we turn to sampling, right? And so we talked about this briefly a few times as we've gone through the book. Is we need to make sure that our samples match the population that we're interested in. And for a lot of scenarios, if you're interested in the height on campus, we can make sure it's not that difficult to make sure that our sampling matches our population, right? We do need to be mindful that we're not sampling people that are walking out of, what did we say, the diving team or the basketball team, right? We need to make sure that we're sampling from the right place, a random sample in that case, or some type of method that kind of mimics random sampling. That's more difficult in something like election polling, and we've known that, but it is important to bear in mind that we can crunch the numbers, and you were I forced you to do that on not only exam but the homework. We can take sampling data and quickly crunch what that means. So the what percentage we expect each candidate to get, a margin of error. We can take that one step further and say candidate A is 63% chance to win the election. But all of that is built on proper sampling and accurate sampling and knowing that the sample matches the population, and that's difficult to do for a few reasons. Now, first and foremost, remember, we want a representative sample, and we want a representative sample of the population, and that's where it really gets tricky with election sampling, especially in a country where it's your choice whether you want to vote or not, right? And so what that means is that we don't know the full population. If, for instance, we were forced to vote, right, or it was mandatory, and there are some places like that, we'd have a better feel for what the population that we're interested in is. But in our case, and most places, it is a choice, and so not only are you trying to measure and sample and do good sampling you're also trying to get a feel for who is likely to vote, right? And so that's why you'll see the likely voter designation. But even with that, we don't know what the end population is until election night, until people go out and actually vote. And so that makes it very tricky. So for instance, if you were paying attention last night, one of the first big story that came out was results in Florida, and Trump doing quite a bit better than maybe the polls had anticipated, and largely driven by, if you remember hearing this, some results down in Miami-Dade County, which has a heavy population of Cuban Americans, and we'll get kind of down on a political science side of things here, but Cuban Americans tend to be conservative leaning. Most of them have direct connections back to Castro, in the situation with Castro in Cuba, and most have some connection of kind of fleeing the Communist Party there. And so they have a tendency to vote very conservative. Now, what we don't know in any election is what proportion of people in any group are going to actually show up and vote. And so what the polling probably got wrong was the level of turnout amongst groups such as the Cuban Americans in Miami-Dade. And so you can do all the best polling that you want and show what percentage of likely voters are going to go for each candidate. But if you don't have a good feel for who is actually likely to vote, the polling becomes problematic. And that's always going to be, again, that's always going to kind of be an issue that we have to fight with. Cat hair in my coffee. So another thing that we might want to think about in terms of polling is, how do we evaluate how well polls do? And there are some methods to do this. So it's hard to do on an individual poll, however. So let's say we have a race, and our polling suggests that candidate A has a 65% chance to win the election. It's hard to know after the race if that was an accurate poll, because, of course, if you have a 65% chance to win, you have a 35% chance to lose. And these are probabilities. Those are going to happen. It's more likely that the candidate wins, but just as, you often will roll a 1 through 4 on a dice, you sometimes will roll a 5 or a 6. And so the simple act of rolling a 5 or a 6 doesn't mean that the dice was, off. It's not a skewed dice. It just is going to happen sometimes. So on an individual level, it's hard to evaluate a single poll. But we do have methods, and so you can think about it this way. If we have many polls, many elections, many different races. So for instance, in like the House, we have 435 House races. If we had a bunch of elections that we all kind of or a bunch of races that we thought came down in a similar range. So maybe we had 50 races where we thought the likelihood of one candidate winning was about 65%. We could then look at our methods afterwards and say, out of those 50 elections, how many of those 65% winners actually won? And our methods should leave us with about 65% actually winning and 35% not winning, right? So in some sense, you can kind of do a distribution analysis of your sample distributions, and that's a method that is employed. And so you'll probably see that if you jump on 538 in the next week or two, they'll probably have some results in kind of trying to get a feel for what their modeling did. And that's probably the most straightforward way to kind of examine polling. It's hard to know right now because there are races still undecided. I think that the general feel is that a number of the polls were overweighting Biden or Democratic candidates, at least slightly. And again, much of that's probably through turnout. You'll probably hear a discussion of maybe the shy Trump voter, somebody that responded to the poll and said, I guess I'll vote for Biden, and then went into the booth and voted for Trump. There is a little evidence that might be occurring a little bit, although it didn't happen very much in 2016, or that's what the kind of the evidence suggests. And it's probably not a driving factor. Again, it's pretty early to know for sure, but I think the data so far suggests that the shift was probably more in terms of turnout among varying groups. So if you just to sum it up, if you went to sleep at some point last night, things have changed overnight. More votes have been counted. Best estimate is that Biden will end up winning. Other estimates, the House is the House is staying in Democratic control. And the Senate is pretty uncertain, probably slightly leaning towards GOP control. But all of those are still uncertain. The House is certain to be Democrat, but the presidency and the Senate are still officially undecided. So that's kind of the short snapshot. But yeah, so I do want to again say, if you have more questions, please feel free. You can shoot them down in the chat, or if you want to send me an email later and we can chat more. And if we do see some of this kind of polling evaluation come out in the next week or two, we'll probably just take a few minutes and talk about that when it does happen. So, yeah, I'm not sure there's too much more to say, since, again, there's a lot we don't know yet. So, with that said, I think we will turn and start talking about Chapter 10. Now, the nice thing moving into Chapter 10 is that we are not leaving behind what we've done thus far. So, the questions and the way we're framing our analysis is going to change a little bit, but we're going to stay in the world of the Z and the T scores. So all of that work you did to cram and study for the exam and to, that's all not for lost. You can use it again here. So to kind of frame where we are, I was going to turn on this, and yeah, to get us back kind of squared away, remember in chapters 6 and 7, we learned distributions, right? Probability distributions. And including in that was the normal distribution, right? That's the first time we came up with the Z-score, the standard normal distribution, or normal distributions in general, right? So we have these normals, and they're in some sense easier for us to handle. We have some methods to deal with it, and of course the big revelation in chapter 8 is all things become normal. Right, in some sense, or when we sample, we can treat things as normal distributions. This feels like a new religion. All things become normal. We could build it around that. So we can apply the normal distribution to all kinds of different scenarios. And in fact, that's what we do in chapter 9. Is we turn to some kind of real world questions that we might be interested in. What is what is the mean of a certain group? And specifically in chapter 9, we deal with what happens when we don't know the mean. How do we take a best guess? How do we build in uncertainty? And of course, we also deal with not knowing the population standard deviation. But most of our questions in chapter 9 are this question: what does the population mean? I'm not sure. Let me take a sample and take a good guess at it. Chapter 10 is similar, except we're going to phrase our question slightly different. Okay, so again, 9 is, I wonder what the mean of the population is. Let me take a sample and get a good guess. Chapter 10 comes at it slightly different. It says, I have a thought as to what the mean might be, or maybe somebody else does. We have a hypothesis of what the mean might be. Let me test that hypothesis. Let me test this claim. So in 10, we're gonna be testing claims or hypotheses. Okay, so much of what we do is going to be similar to chapter 9. We're just going to have, so number 1, we're going to come at it slightly different. The question's going to be a little different. And number 2 is we're going to be a little more structured in how we approach the question. And specifically, we're going to rely back on maybe what you learned back in, I don't know, 6th or 7th grade science. We're going to jump back to the scientific method, and we're going to adhere ourselves to that kind of flow of thought process. And so that's a lot of what's new here in chapter 10 is taking our statistical methods from up above here, chapters 7, 8, 9, and fitting them into the scientific method so that we can use this type of sampling to evaluate different claims. In chapter 11 is just a different it's a different set of questions we can answer, but we're still going to be testing claims. Okay, so we do the same thing in 11. It's just slightly different questions. So we will go through the same in chapter 10 and 11. We'll deal with this same. We'll set it up first as we know standard deviation, and then we'll forget about the standard deviation, and basically the same thing. We move from the Z to the T, and so that's going to be a familiar flow. Yeah. So that's kind of where we are and where we're headed there. So let's talk about this scientific method. Again, this will probably start to kind of refresh. Let me pop it up here. So your book has a pretty good graphic here that kind of lays it out in steps. And I would encourage you that you can return to this if you're working through a problem and you say, okay, what do I need to do next? Come back and make sure that you've done the previous steps. So, okay, I've done step 1 and 2. That must mean I'm on to step 3. And so the first thing I would point out is that this is our sampling up here. Step 5, take a sample. This is what we've been learning, chapter 7, 8, 9, and it doesn't happen until step 5. So a lot of what we're going to cover in this chapter is I'm off the screen, but it's back there in step 1 and 1 through 4. So none of our statistical number crunching really happens till step 4 and step 5. So we have a lot to do before then. So one way to think about, again, what we're going to do here is we're testing claims, we're testing statements. And so, we might say something like, okay, so in chapter 9, we said, for instance, I'm curious what the mean height is on campus. And the way we solved that or got a good guess of it is we said, I don't know what the mean height is. Let me take a sample and that'll give me a good guess. And so we took a sample and then we said, this is my best guess. Let's build a confidence interval. Here, we're going to respond to some type of a claim. So for instance, maybe your friend says, I'm pretty sure the mean height on campus is 68 inches. That's a statement that might or might not be true. We're going to test whether or not that's true. Okay, and so the way we're going to structure this is through the concept of a null and alternative hypotheses. So your friend has made a statement, and that statement is the population mean is 68 inches. And we want to test that statement. And so to do that, we're going to set it up as that statement is the null hypothesis. We're going to indicate that with an H hypothesis and then null being 0. So H subscript 0 there. And we'll just say, again, the claim is that the population value, mu, is 68. So if that's true, then the null is correct. Alternatively, or the alternative hypothesis, so H subscript A, let me make sure you can read that. The alternative hypothesis will set up as the population value is not 68. And this is step one. We need to set up our null and alternative hypotheses. Now, this is our first decision. What we have written here is what we call a two-tailed test. Two-tailed because we don't care if it's above or below. We're interested in whether or not we're interested in if it's 68, that can be true, but if it's wrong in either direction, the alternative, we'll go with the alternative and reject the null. Okay, so if this is truly 68 here, and we'll be thinking in terms of normal distributions, so the two-sided test is going to rely on both directions, okay, because it's set up as mu is equal to 68 or not equal to 68. So let's look at the other scenario here. What if your friend had said, I think the mean is greater than or equal to 68, or maybe they said it's at least 68. I realize I'm kind of off the screen there, or behind my... So a statement of the mean is at least 68 suggests that they're not wrong if the mean is in fact 72. Right? So in this scenario, we would consider that statement wrong only if it was less than 68. So this we refer to as a one-tailed test because, of course, they're only wrong if it's less than 68. So on the one side of things. So this is a decision that we have to make when we set up our hypotheses. And sometimes, again, if the statement is at least 68, that's pretty clearly a one-tailed test. Sometimes it's more ambiguous. I think oftentimes we want to default to a two-tailed test unless we have reason to think it's a one-tailed test. So again, in this case, we would have reason to build it as a one-tailed test. If the statement was at least 68. But if the statement is, I think the answer is 68, then it's a two-tailed. So we'll get more practice with this with some examples. But that's kind of the first kind of decision that we have to make. The second decision is the level of significance. The level of significance is going to feel very familiar because it's kind of the other side of the coin of confidence interval, or it's built very similar to the confidence interval. The only difference is, not the only difference, but the main difference or how it presents itself is going to be the flip side. So it's when we dealt with confidence intervals, we were talking about kind of the range inside, right? So a 95% confidence interval was all about 95% inside these kind of values. Here, of course, what we're focused on is values outside of a certain range. And so this is a 95% confidence interval. But what we're going to deal with is level of significance, which is the outside side. So this is going to be 0.05. And we use alpha to indicate the level of significance. But the rationale 5% and 95% well together here. So you can kind of think, in fact, you'll see the same values popping up. So for instance, a two-tailed test, 95% confidence interval. You probably recall when we looked at the z-table, that was a 1.96. Similarly, a 5% significance level with a z-score is 1.96. So the same process going to the z-table, looking up our percentages and finding the z-value is the same. It's just the flip side of the coin. Now, of course, this changes slightly when we go to a one-tailed test. So in that case, just like, so it's going to change a little bit, but it should be, we'll again have experience working with one-tailed test. So, yeah, I'm going to erase my one-tailed example just so we can focus in here. Now, step 3, we'll come back to step 2 here in just a second, but step 3, we're going to identify the test statistic, and that comes down to what do we know, right? So this is where we're deciding, basically, are we dealing with Z or T, at least in our examples. Okay, so there are other, obviously this 6-step process can work for other methods. So it's not just about this, but largely what our decisions are going to come down to is, do we know the population standard deviation or not? And when we do, we can use Z. When we can't, or when we don't, we use the T distributions. And the same process results, right? So T distribution, we need to know the sample size, adjust for degrees of freedom, and so on. Now, okay, so we do have to decide Z or T. Okay, and that's largely step 3. Now, going back to our levels of significance. One way to think about level of significance is how much evidence do we need to say that the null is not right, or the null is to reject the null, right? So again, our friend has stated we think the mean, or I think the mean is 68 inches. And really the process that we're going to go through is, all right, let's assume that your friend is right. Can we find enough evidence to say that's not a true statement, or we're going to reject that statement? And that's the process that we're going to go through. Okay, so what we have to decide is how much evidence is enough. And that's really what the level of significance is after. Is a 5% enough evidence, or is a 10%? So a 10% level of significance is a lower bar of significance, or a lower bar of evidence that's needed to say, my friend doesn't know what he's talking about, it's not 68 inches. Whereas when you raise it to a 5% significance or a 1% significance, we require more evidence to reject the statement. So again, and this is not necessarily a natural way to think about it, but we often start with, let's assume the null is true. And if it were true, do we have any evidence that says it's not? Or it's unlikely to be? And we set how much, we want to set up the bar, how much evidence do we need to reject this statement? And again, we're doing all of this before we ever get to taking a sample. Okay, and that's important, especially with regard to the scientific method, right? We get into pretty shady ethical statistical methods here if we start messing around with the order of these steps. And in fact, that happens. And so we can talk more about some of those pitfalls later on. One good corollary to maybe help you understand what we're actually doing here, or kind of what the process we're going through. So another way to set up, or another null hypothesis, and this will age me a little bit because I doubt many of you were born at this point, but so you could write a null hypothesis as OJ is innocent. Okay, and in that case, the alternative is OJ is guilty. Okay, so obviously we can't test this with sampling. But the concept of null and alternative hypothesis, I think, work here, especially when we think about level of significance. If we think about level of significance as a measure of evidence that we need, it pairs quite nicely with our criminal justice. So we assume that a defendant is innocent, right? Regardless of what we think of their innocence or not, we always start from the baseline that they are in fact innocent, and now let's see if we can prove or show enough evidence to suggest that they're not. Similarly, our friend might have made a silly statement. So this is what, 5'8"? It's not that crazy of a statement. But if your friend says, I think the mean height is 78 inches, that's what, 6'6". Your friend, we all know your friend is probably wrong, but our process is going to assume that they are right. Okay, so regardless of the statement, we still start from the vantage point of OJ is innocent, the statement, the null hypothesis is true. Let's start there. Now, prove to me or show me enough evidence to overcome kind of my hurdle or my bar of necessary evidence. And that's what we're setting with the level of significance, right? So kind of a high jump bar. Maybe this is the 0.10. If we want to raise that up, a higher bar, this might not make sense, but a higher bar, tougher to get over, is a 5% significance. Okay, and so again, much like confidence intervals, where we said it's often 95, sometimes it's 90, sometimes 99. We see the same thing with levels of significance. Sometimes we have 1%. Typically, 5% is a pretty common. But what I'm trying to say is, we set that bar, and then we show or look and determine if there's enough evidence to clear that bar. Just like in our criminal justice, right? What is the term? I'm not a lawyer, but it's beyond a reasonable doubt, right? So we say, all right, OJ's innocent. Can we prove beyond a reasonable doubt that he's guilty? And just to clarify, this is why the Kardashians are famous. Maybe that puts it more into context. Yeah. So that's the running back that I'm talking about, the one that is associated with the Kardashians. So, but what did we show, or what ended up happening through a whole convoluted scenario? At least the jury said there's not enough evidence to say that OJ is not innocent, to reject the null. Okay. Now, the level of evidence needed is important here. So one thing you, again, may have noticed, I think there was a Netflix special, so maybe you've seen that. The level of significance is different in criminal court versus civil court. So civil court has a lower bar, and I forget the terminology for it, but it's a lower bar of evidence that's needed to reject the null. And so OJ was actually, is convicted the right term in civil court? I'm not sure. He was found liable. I think that's the right term. OJ was found liable in civil court, mainly or partially because there's a lower level of evidence needed. And so he owed a certain amount of millions of dollars to the family of Nicole Brown. And so one way to interpret that is that they were able to clear the lower bar in civil court compared to criminal court. So that's just a way to kind of frame what we're trying to do here. Similarly, we're going to say we think our friend is right, or we're assuming they're right. At the mean is 68. Now let's examine the evidence. And in this case, our evidence is going to be, we're going to take a sample. But let's examine the evidence. Can we find enough to clear this level of significance? If we do, we will reject the null and go with the alternative. If we can't, we will just then say we can't reject the null. And so our friend may be right. Okay, so we have our null and alternative. we've chosen a level of significance. Let's say it's 0.05. Let's say in this case, we know that the mean is, or sorry, not the mean, the population standard deviation is 5. Again, in this scenario, we probably don't know that, but we will see a number of examples where we do know the population standard deviation. Specifically, we'll go through some kind of factory sampling tests where we would know the at least a good feel for the population standard deviation. So if we know that, we can then turn to step 4 and formulate a decision rule. Again, because we know the sample, or again, because we know the population standard deviation, this means that we're likely using a z-test. So let me get out of the way. So when we then know that we are interested in the z situation, and what we're going to do in step 4 is formulate a decision rule, and we're basically going to find out what values the sample mean could be for which we would reject. Okay, so we are going to take a sample in step 5 and find a sample mean. We're going to find a sample mean. What we're doing in step 4 is we're kind of pre-doing the math. We're crunching the numbers to say, when we do get a sample mean, do we reject or not? Okay, so excuse me, working off of the z formula, we have this formula. Okay, so let's plug in some things. Two-tailed test, alpha of 0.05. Again, that's going to be that familiar. We can look it up on the z table, but that's that 95%. It's going to get the same value as the 95% confidence interval. And so that is 1.96. Okay, so z of 1.96. Basically what we're saying is if we take a sample mean and we find a value greater than 1.96 or less than negative 1.96, we're going to reject. And all we're doing here is we're transferring, or we're blanking on the word. We're turning this 1.96 kind of cutoff into what the sample means would be. So let's fill this out. So again, we're working with the assumption that our friend is right. So this is 68. We've said we know that this is 5. The standard deviation of the population is 5. Okay. And then lastly, we do need to know how big of a sample we're going to take. So we haven't taken the sample, but we should be aware of what it is. And so let's say we're going to sample 100 students. Now, we can now solve for x bar. Again, this isn't going to be what our x bar is, but this is the cutoff value, or what we refer to as the critical value, for which if it's beyond that, we're going to reject the null. So let's quickly just finish this out. So 1.96, I'm going to multiply by the 5 over square root of 10, which is 5 over square root of 100, which is 5 over 10. X bar minus 68. Now, a couple things to note. We are doing a two-tailed test, so we're interested in if it's in both directions. Okay, so let me zoom up here. So in some sense, there's a positive and a negative z value here that we're interested in. So this becomes 0.98. I ran out of space. .98 equals x bar minus 68, though there's kind of an implicit plus or minus here, right? So basically what we're saying is if we are 0.98 away from 68, that's going to be enough evidence to say, hey, this sample mean suggests that the null is not right, and we're going to reject the null. So we could say if we get x bar greater than 68.98 or x bar less than 67.02, right? So I'm just subtracting. Good question. So the 5 over 10 simply comes from this being pulled up, right? So the bottom, I'm just pulling it up. I'm taking the square root of 100. So we're, in this sense, we're just kind of solving for x bar. Okay, and so we want to know, basically what we're trying to find out is, before we run the sample, what are we looking for? And here we found these critical values. And so now when we turn and take the sample and it shows, we sampled 100 students and we got an average of 66.7. That is outside of our critical values, and so we're going to reject the null. Or if, for instance, we took the sample and it came out at 68.4, that's within this window, and so we're not going to reject the null. And so that's really the process, and we're right back to taking a sample, crunching the z-scores, right? And so much of what we're doing here, as far as the actual statistical mathematical work, is pretty familiar by now. Again, I note that we're kind of going at it a slightly different direction, but hopefully it doesn't take too long to kind of sink our teeth into this. I think oftentimes the trickier part is to kind of keep track of all of the steps along the way. So we'll have more chances to run through some examples. So what we've done here is just step 4. So we've set up our critical values, our decision rule, and our decision rule saying here is that if we find an x bar greater than 68.98 or less than 67.02, we will then reject the null and say our friend is wrong. The mean is not 68. But if we find something in between there, we don't have enough evidence. Okay, so in similar sense, we've set up how much evidence we need to find OJ guilty or not. And that really turns us into step 6. Once we've looked at the sample, how do we interpret that? And again, that's all about whether or not we can reject the null or not. And we'll have more practice with this as we see more examples. But I want to, before we spend a lot of time on that, I do want to take the last kind of 10 minutes here and talk about another big concept that we are being kind of exposed to here, and that is of errors, and specifically type 1 and type 2 error. Because I think that this also takes a while to sink in, and so it'll be helpful for you to see it right away. So we can think of possible outcomes in this scenario being one of 4 situations. So let me just kind of zoom this up. When we take a sample, in this case, we are trying to find the truth of the situation. So we're trying to find whether or not the mean is actually 68. But the truth is out there, right? So X-Files fans, again, that's so old. That's as old as OJ. But the truth is out there, and so in reality, the null is either true or not, right? The mean is either 68 or it isn't. OJ is either guilty or he's not. Okay, but when we run our process, what we find is not always going to be the truth. We hope it is, but sometimes it's not going to be. So do not spell not right. Do not reject the null and reject the null. Okay, and so we would hope that these match up, in that if the mean is 68, right? So if the mean is 68, then the null hypothesis is true. We would hope that we find that, in fact, we don't reject the null. So we want to be here, right? So correct. If, in fact, the null is true, we hope that we find it's not true. Similarly, if the null is false, if it turns out that the population mean is not 68, we hope that we can reject that null and be down here. Now, of course, we don't know, and so our process is going to be to take a sample. And we know with sampling comes sampling error, and we might randomly find we might randomly find a sample mean that is very far away from the population mean, right? We've talked about, and that's really the basis of our confidence intervals, is that we can only be certain level of confident because we do occasionally find these kind of extreme samples. Similarly here, we might find the wrong answer. So the mean could be 68, yet we find randomly a sample mean that is 66.5, and it's enough evidence, and we reject the null. So we end up here, right? And so we have what we call a type 1 error. Okay, so we have rejected the null. We've said our friend is crazy. It's not 68, when in fact it is 68. And that's not an ideal place to be, right? We've gotten it wrong. We can also get it wrong in the other direction. So again, this is under the scenario that, let's say that it's not 68. Let's say the mean is something else. Maybe it's 70, maybe it's 63. I don't know what it is, but it's not 68. But when we take the sample, we get something pretty close to 68. Our sample mean is 67.8. So we say, well, that's close enough. We can go with the thought that it's 68. That is what we call a type 2 error. Again, not a great place to be. Now, whether we're concerned more about type 1 or type 2 depends on the scenario. And in some regard, when we set our alpha, we're making some form of a trade-off between the chance of being a type 1 or a type 2 error, right? So when we set a certain bar in terms of the evidence that we need, it adjusts how likely it is that we find to reject the null or not. And so that's going to impact our likelihood of having type 1 or type 2 error. This concept of type 1, type 2 error takes a little time to kind of percolate through. Depending on where you are in statistics or what field is using the statistics, you'll see this referred to in different ways. One of which, and this might have been what you heard more, is what's called a false positive or a false negative. And specifically, we've heard this in COVID testing. So undoubtedly, you've heard these terms talking about people that got a positive test result, and then it turns out that either they ran the test or anyway, they didn't have it, so that would be a false positive. So in medical literature, it's often that framed in that sense. But it's the same concept in the same kind of Punnett square here. And so I'm going to try to pull this up as another way to kind of think about what we're doing here. Let me get out of the way. So kind of a silly example, but we have here, so the pregnant, let's formalize our null and alternative here. So the in this case, the null, let me change colors here. The null is going to be off the screen. The null is you're not pregnant, right? And then if we find enough evidence that you're pregnant, then we say that we're going to reject the null and say you're pregnant, right? And that's what a pregnancy test does. Either home or here at the doctor's office. We start with the baseline that you're not pregnant, and we test and you find out. So what's happening in the first window here? obviously this gentleman is not pregnant, but the testing has shown has rejected the null, right? And so we're up in this window, right? The null is true. The truth is that he's not pregnant, but our testing rejects the null. And so we have a type 1 error or a false positive. Okay, and on the flip side, we can see the pretty obviously pregnant lady is being told that she's not pregnant. And so we're down here where the I realize I have a little error here. So this should be HO is false, right? So the I think I had HA there, but so the null is false. So she is pregnant, but we're getting a do not reject, and so we are down here in type 2 error, okay, or a false negative. So again, which one is more important really depends on the context. In this case, it's probably better to err on, we might want to err on false positives or have more false positives. We probably don't want to tell a woman that they're not pregnant when they are. Obviously, this is a silly example, but something like an at-home pregnancy test probably errs quite a bit on avoiding type 2 errors. They want to make sure they don't miss those, right? Because there's behavioral changes that come, and you don't want to say you're not pregnant and then go, party it up or something. And but again, that's dependent on the scenario. So we're going to talk more about kind of this trade-off, and a lot of it again revolves around what level of alpha we set. And specifically this again translates, and maybe we'll talk about this on Friday, but think about OJ or just criminality in general or criminal cases. There's kind of we trade off type 1 and type 2 errors in terms of, do we send innocent people to prison or do we let guilty people walk free? And where we set that level of significance in terms of criminal justice also trades off type 1 and type 2 error. And we tend to lean more heavily, again, on making sure innocent people don't go to jail, although that definitely happens. But yeah, so this trade-off applies not only in our statistical methods. So that's really what we are focused in on here in chapter 10. And again, chapter 11 is going to follow a similar flow. It's just we're going to compare two samples instead of just one. But hopefully this gives you kind of a framework as to what we're trying to accomplish here in chapter 10. And again, there's a lot going on. Don't wait till next Tuesday to get into it. But so you can look for some videos over the next few days, and we'll be back on Friday right here again, and we can walk through some examples and see it in action. So I will stick on here for a minute or two, or if there's questions, we can stay on longer. But otherwise, I also have office hours, so if you want to jump in, feel free from 1:30 to 2:30. Otherwise, we'll see you soon.